Hello everyone, my name is Tejas Yi and I am an undergraduate researcher at UCLA's Jalali-Lab. Today I will be presenting on my work regarding physics-inspired low-light enhancement for smart vision on the edge. As is alluded to in the title, my goal with this project is to showcase the capabilities of physics-inspired computer vision, or PhyCV, algorithms in the context of edge computing, and demonstrate how PhyCV can improve the performance of object detection networks and automated tracking systems, especially in low-light conditions. This video is part 1 of a 4-part series and introduces the PhyCV framework and algorithms, as well as my project description and problem statement. If you are interested in building off my work or recreating my results, make sure you stick around until the end of the series, as I will be explaining how to use my repository and tools in the final video. In this video, I will be covering the general introduction to both my project and PhyCV. I will start by explaining what PhyCV is, as well as outlining my project goals. Next, I will describe some motivation and advantages of the PhyCV framework. Finally, I will conclude with a description of Vivid, PhyCV's low-light enhancement algorithm, which is the main focus of my project. The main goal of my project is to demonstrate how PhyCV can enhance the performance of computer vision applications on the edge in low-light environments. To demonstrate this goal, I implemented an accelerated version of the Vivid algorithm optimized for use on the Jetson Nano, a small single-board computer developed by NVIDIA. I then integrated the algorithm with NVIDIA's Jetson Inference object detection library to enable real-time object detection on a live camera feed. Finally, I connected a pan-tilt-zoom, or PTZ, camera to the Jetson to showcase improved object tracking in low-light conditions. In summary, this series of videos will focus on one of PhyCV algorithms, vision enhancement via virtual diffraction and coherent detection, or VIVID, and showcase both its performance on NVIDIA's Jetson Nano while running in concurrence with object detection models, and its ability to enable improved object tracking accuracy of a connected PTZ camera. First, why is this an important problem? Well, with the explosive growth of image and video data, object detection algorithms have become indispensable tools for automating tasks and enabling innovative applications. From autonomous driving to security and surveillance, modern systems are becoming increasingly reliant on efficient and accurate object detection networks. However, current object detection algorithms still have limitations. In the context of image processing, low-light environments negatively impact the quality of input images, resulting in decreased contrast, loss of fine details, and increased noise. This can cause object detection models to struggle differentiating objects from backgrounds, or even to misinterpret noise artifacts as objects themselves. PhyCV presents a solution to this problem. Its algorithms are fast, memory efficient, and can be integrated into most object detection pipelines with little overhead. Now, you might be wondering, why not just use machine learning for low-light enhancement? Well, here are some important factors to consider. First, as the Internet of Things, or IoT ecosystem expands, edge computing becomes increasingly necessary in handling the massive volume of data generated by IoT devices. However, machine learning-based low-light enhancement algorithms encounter several challenges when running on low-compute edge devices. Neural network models can consume large portions of memory, limited computational resources can result in slower inference times, and the energy consumption of complex machine learning algorithms can quickly drain device batteries. In these important areas, Vivid dramatically outperforms its machine learning-based low-light enhancement counterparts. Since it is based on physics, contains fewer parameters, and additionally requires no training, it is not bottlenecked by the same factors as machine learning algorithms. Because of this, even on low-compute, low-memory chips, it is possible to pre-process input frames with Vivid before running a detection model. As you can see, Vivid is orders of magnitude faster than 0DCE, a state-of-the-art neural network for low-light enhancement. So, how is PhyCV able to perform such high-quality image processing tasks while being so efficient? The key is in the framework and approach used in its derivation. PhyCV is unique because it leverages the physical laws of nature as blueprints for its algorithms. Equations of physics are great at modeling complex phenomena in a low-dimensional manner. For example, take the classical physics equation F equals ma. This equation contains only one parameter, the mass, but still predicts a wide variety of phenomena. This approach produces several salient advantages when compared to the current landscape of image processing approaches. For example, in comparison to deep learning algorithms, PhyCV can achieve similar performance, but is orders of magnitude faster, as seen in the previous slide. When compared to traditional algorithms, which are a sequence of handcrafted empirical rules, PhyCV produces far better results, making it a more powerful tool for computer vision applications. More specifically, PhyCV algorithms emulate the propagation of light through a physical medium with natural and engineered diffractive properties, followed by coherent detection. The diffractive medium will apply a phase kernel to the frequency domain of the image and convert a real-valued image into a complex function. After coherent detection, the output phase contains useful features of the input image. Now let's dive a bit deeper into the mathematics behind Vivid. We will start by examining the unified framework for photonic time stretch, seen here to the right, from which the PhyCV algorithms are derived. The core steps here are the information modulation, in which the incoming information is modulated onto the optical spectrum, and the information stretch, in which the spectrum is manipulated in accordance with the physics of optical dispersion. The information stretch step gives rise to the 1D continuous time stretch operator, seen here in red. Converting this operator to the discrete domain, extending it into 2 dimensions, and switching from temporal to spatial coordinates, making an analogous physical process diffraction instead of dispersion, gives us the 2D discrete stretch operator, from which Vivid is derived by using spectral phase filter with a low-pass characteristic. Using a low-pass filter as a phase operator is what gives Vivid its low-light enhancement power, as regions in the image with low spatial frequency are boosted by this phase operation. Something interesting to note is that this framework is great at mapping the data from a domain in which it is difficult to differentiate important features, i.e. the problem of measuring extremely fast signals or the problem of low-light enhancement in 2D images, into a domain in which the features are easily differentiated. Optical dispersion spreads out the Fourier content of the signals so features of fast signals can be detected, and spatial diffraction with the low-pass phase kernel allows regions with low spatial frequency to have their Fourier content boosted, resulting in low-light enhancement. To further accelerate the low-light enhancement process, Vivid Light was introduced, which is a numerical approximation of the full Vivid algorithm. This approximation removes the forward and inverse Fourier transforms in the original Vivid algorithm and replaces them with a closed-form approximation in the spatial domain. This further reduces the computation time without sacrificing the visual quality of the output. Here we also compare the achieved frame rate of low-light enhancement by 0DCE, Vivid, and Vivid Light. We can notice that Vivid Light reduces the number of tunable parameters from 4 in the full Vivid algorithm to 2. Unlike the neural network approach, Vivid's parameters do not need training, and an optimized choice of parameters works well for a wide variety of images. In summary, this video introduced PhyCV, a novel class of physics-inspired computer vision algorithms developed in the Jalali-Lab at UCLA, and outlined some of its most important advantages in the context of image processing and computer vision applications on the edge. If you would like to learn more about the implementation details of my project, namely how I built an automated tracking system using a pan-tilt-zoom or PTZ camera controlled by the Jetson Nano, make sure you stick around for part 2. Thank you for listening.